Everyone, my name is Victor Flamini, and Senior Design Team 8 will be presenting a portable brain-computer interface for ALS patients. I'm joined today by Huang Nguyen, Angela Giuliano, and Cody Stevens. And ALS is a degenerative neurological condition that affects nerve and brain cells, and importantly causes a lack of muscle control. It's fairly common. 1 in 400 people in the US and Europe will develop over the course of lifetime, and people with ALS really cannot do mundane tasks without assistance. So some of our goals are to restore autonomy while keeping it in a convenient manner, understanding economic, social, and comfortability factors, and also develop a non-intrusive solution that allows patients to remain connected with their environment. So one solution that can accomplish this is BCI. So BCI is a computer-based system and acquires brain signals and analyzes them, translating them into a desired action. So it's designed to capture intention directly from the brain with multiple options for input stimuli and, importantly, no muscle movement required. Now, there's still some issues with BCI as they usually require a large screen for stimulus displays, and that can drain attention from surroundings and make the user feel isolated from the environment. So an example of this is the ALS Hope Clinic's current solution in use with Dr. Terry Hyman Patterson, and he uses a traditional EEG device, as you can see in the image on the right. It is feasible for in-home use, but you can see those wires. You have the laptop PC, the acquisition device, and the monitor can all cause for a complex setup and really require attention to that large monitor over an extended period of time. And like I have been repeating, it can really isolate the user from the surrounding environment. So an updated solution is an augmented reality solution with an immersive visual output display. This is ideal for BCI as it keeps patients immersed in their surroundings and was actually developed in Dr. Ice's lab last year. Now, there's still some problems with the solution. The AR headset is physically large, heavy, and clunky, really a problem for ALS patients who have trouble even holding their own heads up. It has an extremely high cost, which makes it prohibitive for widespread everyday use. And then current AR headsets are designed for gaming. This makes them require powerful graphics and advanced computing in order to function. So our objective is to design and develop an immersive display to integrate with a brain-computer interface while making it portable, practical, and low cost.
So for constraints, we separate them into 5 different categories: time, budget, resources, size, and specifications. Our project is limited to 3 months for planning and designing, 6 months for programming and creating a prototype. The total cost for computing device and display for our project has to be below $500. Our resources are limited to Drexel Labs and ALS Hope Foundation Lab. The size of the device must not interfere with users' abilities to sit in a wheelchair or lie down in bed. We also have to use the Unicorn EEG cap for the brain signals, as well as the BCI software developed by Dr. Aya's lab. The device also has to have the ability to present 6 possible commands and relay selected to users. For display requirements, the display has to have at least 30 Hz refresh rate because the clear difference in frequency can help patients choose the design option easier. Based on the distance between the eyes and the existing AR glasses, the display needs to be placed at most 2 centimeters in front of patient's eyes. In order to maintain the field of view of the patients must have at least 80% of normal vision or 90 degrees diagonal fields of view. The display size also needs to be less than 2.5 inches, as well as having the display hardware weight less than 6 ounces. And for the purpose of this project, the display cost needs to be kept below $50. For computing requirements, in order to maintain the functionality of OpenVibe in real time, the CPU clock speed of the computing components has to be at least 1.4 Hz and at least 4 gigabytes of RAM. It also has to be able to process the EEG data in less than 1 second. And in order to keep the system portable, the battery needs to last for at least 1 hour.
The current AR solution being used by ALS Hope Foundation utilizes 2 computational devices. The large laptop or PC is necessary due to the large graphical needs of the AR headset. Most of the signal processing is done by this large unit, and the Raspberry Pi is used to complete smaller tasks. To simplify the system, we chose to design a new pair of low-profile AR glasses that do not require a large graphics card to power. This allows us to use a small single-board computer as the processing component for the system. The computational device we use is the Raspberry Pi 4B. This is currently the most powerful Raspberry Pi on the market with its 8 GB of RAM and 1.4 GHz of processing speed. We chose a 26,800 milliamp hour portable battery pack to power the system on the go. And for our transparent screen, we adapted a 1.8-inch TFT LCD screen to be transparent. In order to make this unit transparent, we had to remove the front polarizer attached to the screen via adhesive. Then we had to peel off the backlight and its accompanying housing so that there was nothing behind the screen itself. Once removed, the only piece remaining are the screens attached to the PCI by a ribbon cable. This schematic shows how the Raspberry Pi communicates with the display. The Raspberry Pi GPIO header is connected to the GPIO header of the PCI for the display via jumper cables. The driver controls for the display are controlled by an API on the Raspberry Pi.
So the second part of our project involved getting the programs currently utilized by Dr. Ayaz's team onto the Raspberry Pi. And the challenge in this came from compiling and building all these programs on a singular environment that was supported by Raspberry Pi. And this wound up being an Ubuntu 18 operating system. So in order to acquire the signal from the Unicorn, we used an API developed by the Unicorn EEG headset developers to write a custom app in C that could communicate with OpenVibe, which is the EEG signal processing program that also does BCI classification and produces the stimulus. Now, the stimulus also would be drawn to the screen. In order to do that, we wrote a custom image drawing program in Python that utilized an API designed specifically for the drivers that our screen interacted with on the Raspberry Pi.
Here's a demo video of our system working. So as you can see, the user is sitting here wearing the Unicorn EEG cap along with our low-profile AR glasses. These glasses are connected to the Raspberry Pi via the jumper cables, which is connected to our portable battery pack. So the display continuously displays the GUI showing 6 options. The user focuses on their desired choice to make their decision. OpenVibe is continuously recording EEG signals in order to determine when the decision is made through the EEG cap. So this is showing the acquisition of data. Once the decision is made, an icon shows up on the display showing the user which decision was made.
For our verification testing, we started out by testing our display screen. We want the display screen to have a minimum refresh rate of 30 Hertz so that there's an easier selection for the user. And for optimum placement, we want the screen to be no more than 2 centimeters from the user's eyes. We want the field of view to be at least 90 degrees because that'll be at least 80% of a human field of view. And with the screen size to be less than overall 2.5 inches. And the hardware, including everything in the glasses, should be less than 6 ounces. Our first testing was to make sure that the refresh rate is greater than 30 Hertz. In order to do this, a script was used that had a finite amount of images that, when played, created this animation of a ball moving across the screen. The script had timed the amount of time it takes for these animations to play, and the total number of frames over the total time was used then to calculate the frames per second. These are the results from that test, and the average that was computed was 39.116 frames per second, which meets our requirement and is well above the 30 frames per second that we were going for. And that makes sure that the icons that are flashed are identifiable to the user. The next test was the field of vision. Our goal was to have at least 90 degrees, which again is 80% of the normal eye's field of view. In order to do this, we had the subject stand 3 feet away from the reference point, in our case, a wall. The subject was then instructed to close one eye at a time and mark certain points on the wall to test the total span of their vision. And then that information was plugged in. The horizontal distances over 2 times the vertical distance yielded the total field of view for each eye independently. The right eye had yielded just under 80%. We had a total percent of vision of about 71.6, which was short of our goal of 80% normal vision. And the left eye was successful, and we had about 83.1% of our normal vision and does compensate a little bit for the vision that was lost in the right eye. The dimensions of the screen fall across our parameters as well. We wanted the screen to be no larger than 2.5 inches. We have a 1.26 by 1.64 inch screen, which is about 1.8 inches diagonally. And the distance from the eye is about 1.5 centimeters, which is well below the 2 centimeters that we were going for. The next verification testing we did was in order to ensure that our computation was running correctly. We wanted a minimum of 1.4 gigahertz processing speed and 4 gigabytes of available RAM. The battery usage, we wanted the battery pack to last at least 1 hour and to make sure that it was worked efficiently under normal operation. And we wanted processing time to be close to real time and processes to be less than 1 second. At the end of the system, everything was checked and a just general overall functionality check was done. Our testing was done by doing accuracy testing on 4 different users. Each user did 25 different trials. The trials consisted of the user being told to pick a specific icon off of that GUI, and the user would pick the icon, and then we would record whether they were right or not. The users tended to be right 80% of the time, and we monitored all in this test. We monitored accuracy, processing time, CPU usage, and battery usage. With each trial, we measured the CPU usage and RAM of the system. The GUI display ended up using on average about 19.1%, while the open source OpenBite system used about 50.4% of the CPU and 18.5% of the RAM. The overall processing time was about 504 milliseconds, which is well below our goal of less than 1 second for real-time processing. And the span was anywhere from 480 to 560 milliseconds. The battery also exceeded our minimum. We had a goal of at least 1 hour, and after a 45-minute test, we found that about 20% of the battery was drained. We were then able to estimate that about 3 hours and 45 minutes would be the expected battery life of the system operating at full power.
So from a verification testing, we discerned that our design was a success. Importantly, we were able to maintain a high frame rate over 30 frames per second. And our dimensionality requirements also passed. Our only fail was the 80% total vision, which we saw less than. While this is a little bit smaller than we would have liked to see, just qualitatively speaking, when you put on the headset, it's not as much of a hindrance as we thought it would be, especially considering what the transparency of the screen grants you as far as what your vision is. And then here, all of our requirements passed again. Importantly, we kept the display cost down. $10 is very marginal, especially in comparison to what current systems cost. And then we were able to process the EEG data in less than 1 second, about half a second at 80% accuracy, while still maintaining a battery life of at least 3 hours and 45 minutes from our extrapolation. Moving on to our innovation significance, we designed a low-cost and functional augmented reality system that's going to allow people to stay environmentally immersed. And on top of that, we also simplified the computing system that is involved in the BCI. So the significance this is going to have is really social interaction. People who are more immersed in their surroundings, not staring at a screen. I'm sure you can even relate from looking at an iPhone screen. If you're not staring down at your phone, you're more immersed with your surroundings. You're more likely to interact with people, and that can apply here as well. And then, of course, the restoration of autonomy, which is really important. These people are they're really bedridden, can't do much for themselves, and being able to get that back is a huge factor for them being able to live fulfilled lives.
One of the biggest challenges we faced was trying to work with group members located all around the world. In order to make this work, we had weekly Zoom meetings to discuss problems and goals. We also had some issues with our 3D printer, where the slicer for the printer would not produce files in the right format for the printer. We had to install a plugin to a third-party slicer to try to get the file format that we needed. Also, issues with the print bed adhesion slowed us down. Lastly, we had a lot of issues with installing OpenVibe onto Ubuntu. We had to rewrite the build scripts to compile updated dependencies for the system. And for future revisions for the system, we would include a hands-off and on switch, longer battery life, and fully integratable with at-home devices such as Alexa and Google Home. Along with that, new screen setup should be explored, looking at effectiveness at different distances from the face, number of screens used, and new OLED technologies.
We would like to give our special thanks to Dr. Hassan Ayaz and Dr. Terry Hanman Patterson, as well as our instructor, Dr. Jamie Dougherty, along with other students and co-ops at Temple Brain Computer Interface Lab. And that's the end of our presentation. Thank you for listening. Is there any questions?
I'm Cody Stevens. My concentration is biomechanics and human performance. And in this project, I designed all the 3D models for the display case in Creo Parametrics, as well as 3D printed all the CAD models on our personal 3D printer. I assisted in the conversion of the standard LCD screen into the transparent LCD screen that we use in our design, and I also assisted in construction of the display prototype. I contributed about 30 plus hours of presentation and report development for our final report, and I organized the group members and distributed project tasks for the members to keep everybody on task. The most challenging problem that I faced was actually with the 3D printer. So the slicer provided by the Dremel 3D printer lab did not format the files in the correct file type. This prevented the file from being read by the printer and actually producing the models. So I had to work with a third-party company to identify a plugin that would correctly format these file types. The new slicer needed to be installed, and the plugin had to be installed into that new slicer, and this allowed us to print multiple prototype iterations and test-made design iterations. For the next career steps, I am currently applying for jobs in industry where I can work with 3D modeling to produce medical devices. Eventually, I would like to work for a company that focuses on developing prosthetics, and I tell myself I want to further my education and get my master's at some point, but we'll see how that goes in the next couple of years.
The contributions for Angelo Giuliano consisted of helping with the overall project system design and its implementation. I was also responsible for the verification testing protocols for both display verification testing and the computation verification tests, as well as the documentation of all testing protocols, the system design, build, and the system results. In addition, I helped troubleshoot both hardware and software issues throughout the entire project and aided in the system build where needed.
So for my contribution, I acquired the needed hardwares for the project, especially the Raspberry Pis and the battery packs. I also installed and troubleshooting the Ubuntu and OpenVibes on Raspberry Pi, as well as testing OpenVibes and on other distributions. I also modified the given programs and data package that are given from Dr. Aya's lab. And I also test EEG signals processing using our existing system. I also document and record the system, device systems.
Hello, my name is Victor Flamini. My concentration is bioinformatics. Just going over my contributions to the project. So key accomplishments, I assisted in the physical disassembly of the LCD screen, and that was just to make it transparent and make sure it didn't break while we were making it transparent, which happened a couple times. But I also determined the pin layout for the GPIO access pins from the LCD PCI board to the Raspberry Pi. And this wasn't trivial, just like looking up a diagram of how to do it, even though I looked up many diagrams. I had to kind of like scour some blogs and do some trial and error to figure out which pins went where on the 40-pin header on the Raspberry Pi from the board that the LCD screen came with. Then I also had to determine which driver support for the LCD screen existed for the Raspberry Pi. And then I found an open source API on GitHub that supported that driver. So that API was in Python. So then I also wrote Python scripts using the API in order to control what went onto the screen. So had to learn a little bit about the API, but Python I know pretty well, so that wasn't that bad. And then I also built programs used for the BCI onto Raspberry Pi. This included OpenVibe and Unicorn. The biggest challenge here was just finding a environment for them both to run on the Raspberry Pi. I knew I wanted to use Linux because that's what Raspberry Pi uses, but I had to install a couple different operating systems just to kind of see what each would build on. I know like OpenVibe, for example, is not supported on the newest Ubuntu, and Unicorn has a lot of different tools that are built for different operating systems. I also determined a new signal flow process for the Raspberry Pi. And what this basically means is that currently, in the current solution used by the lab, their signal flow process is really just a streaming source goes to the EEG processing program, which outputs a determined selection. But on the Linux system, or the Linux operating system that I put on the Raspberry Pi, that did not support the stream source. That was only built for Windows. So I had to build a new acquisition method for the actual raw signals that were coming from the headset. And so that was probably my most challenging problem, which I guess I'll go over in the most challenging problem section. And then in addition to all that with the actual building and engineering parts, I would say I also spent over 20 hours, maybe well over 20 hours, I'm not too sure, each term on the report and presentation combined, just making sure everyone's ideas were implemented. A lot of different iterations to make sure it was all good. So yeah, the most challenging problem, like I mentioned before, was getting OpenVibe to actually read the brainwaves from the Unicorn headset, and that stemmed from the program that the lab using now only working in Windows, and this being built on Ubuntu. There are a couple of different ways I could have solved the problem, but looking through the GitHub that the Unicorn EEG headset developers had, they actually had an API in C, so I could program in C using their API to build an acquisition program that I could then connect to OpenVibe, because OpenVibe allows you to use custom programs. So I had to, I have programmed C before. It's not my favorite thing to do. I try to avoid it just because it's a little bit complicated, but I had to really brush up on my programming in C. I had to learn their API and also learn a lot about how signals actually come in to the computer. I don't know if it's from every EEG headset or just the specific one with some of the things, but yeah, I had to learn some of that and write this program. And once I overcame this problem, allowed us to finally connect all parts of our system and have a full working prototype. And then my next career steps in terms of goals, I have a job right now, part-time, that I'm taking on full-time after I graduate, just working in industry in the bioinformatics field, gene sequencing, and also doing software development. And I may also possibly look to further my education in the future.